The next symmetry operation that we want to look at for C60 is the inversion operation, denoted by the little I. We can represent the inversion operation in our model by a stick. And we notice that this particular stick starts at one C60 atom, one of the carbon atoms, and goes to the other side. It connects to another one. Now what's important about this connection between the two carbon atoms is that this particular line that connects the two atoms goes directly through the center, and we denote the center by that little line on the stick. And what we could do if we had an infinitely small stick would be to connect all the pairs of carbon atoms in C60, and we would notice that the line connecting them would go exactly through the center, and that the distance from any carbon atom to the center would always be exactly the same. So we are not able to put more than one of these in there at a time because our stick that we're using has a finite width, and if we try to stick 30 sticks inside here to show all the pairs of atoms are connected that way, they would run into each other and we wouldn't be able to see anything. So we could do this for any particular atom in C60. There is a corresponding atom essentially on the other side of the molecule, if we want to think about it that way, that we could connect with this particular type of line. Now, some people think that the inversion operation isn't a very important operation. In fact, you might think that inversion is just a diversion from your excursion. But nothing could be farther from the truth. The intensity of any spectroscopic transition, any transition event that we might see in spectroscopy, is related to this dipole moment vector D. And we see that we take the integral of the ground state times the operator by the wave function for the excited state, d tau squared. So the larger that D is, the stronger the transition will be observed in spectroscopy. If D turns out to be 0, we say that the transition is forbidden. If D is greater than 0, we say that the transition is allowed. In vibrational spectroscopy, such as infrared or Raman, the ground state always has the symmetry of the totally symmetric representation. Exactly what that representation will be labeled depends somewhat on what the point group is, but an example will be something like A1G. So it might be A1 or just A, depending upon the particular point group that we're investigating. But the important thing in any point group is to first recognize which irreducible representation is the totally symmetric representation. As I like to say, all irreducible representations are created equal, but some are more equal than others, and first among the equals would be the totally symmetric representation. Also, our operator, if we're talking about infrared spectroscopy, will transform just like X, Y, and Z. Which particular irreducible representations that corresponds to will depend on the particular point group. Now, if we have a centrosymmetric point group, these will always have ungerade symmetry. We'll talk about what that is in a second. But an important thing to keep track of is that the infrared operator, the electric dipole moment operator for infrared, will always transform in a centrosymmetric point group like an ungerade irreducible representation. In Raman spectroscopy, on the other hand, the operator will transform like xy, xz, yz, x squared minus y squared, or z squared. We can notice that these are all quadratic terms, whereas the infrared operator acts and transforms like linear functions. So the operator for infrared is ungerade, and the operator for Raman is gerade. To save having to write out gerade and ungerade, we very frequently abbreviate gerade as G and ungerade as U. And this is another example where in learning chemistry and group theory, we will improve our knowledge of the German language. The terms gerade and ungerade are only used when we have a center of inversion, when we have the inversion operation. And gerade means that for some particular situation that we are symmetric with respect to inversion. Easy way to recognize this in a character table is that if we look under the column for the I operation, if we have a gerade irreducible representation, the character will be a +1. So symmetric means +1 for a character. If we have something that is ungerade, it's anti-symmetric with respect to inversion. That means if we look down the column that's marked the little I, and we go across to an irreducible representation that is ungerade, we will have a character of -1. So anti-symmetric doesn't mean that it's not symmetric at all. It means that when we do some particular operation, the character for that operation is -1. The character for a symmetric gerade representation or operation will be a +1 because it is symmetric. It turns out for centrosymmetric molecules, we have an easy way of determining when we will have allowed transitions and when transitions will be forbidden. And it turns out that we do not have to evaluate the unpleasant looking integral that we had seen a couple minutes ago. It turns out that all we have to investigate is the integrand, this psi star ground operator, psi excited. And just from the integrand, we can determine whether a transition will be allowed or forbidden. It's helpful at first to look at the multiplication table for multiplying gerade and ungerade functions. So we see that if we multiply gerade times gerade, we get gerade. If we multiply gerade times ungerade, we get ungerade. If we multiply gerade times ungerade, we get ungerade. And if we multiply ungerade times ungerade, we get gerade. If you are familiar with the concept of odd and even functions, you might recognize that this multiplication table is very similar to the idea of the multiplication of odd and even functions. Gerade functions are even and ungerade functions are odd. So we get the same multiplication table. In vibrational spectroscopy, the ground state is always gerade. It's always G. And be sure, this is for vibrational spectroscopy. For electronic spectroscopy, that is not true. So be sure to keep that in mind. So the ground state is always G in vibrational spectroscopy. And then we have two different possibilities for the operator. The operator will be ungerade, U, for infrared, and the operator will be G, gerade, for Raman spectroscopy. We are ready to do our first example. Let's suppose that we have an excited state that is gerade, and we want to see if a transition from the ground state to that particular excited state is allowed in IR. So let's try IR first, and we'll see if it's an allowed transition. If we take the case of infrared, we all know that the ground state is always gerade, so that's no problem. The operator, up here, is ungerade, and the excited state we're proposing is gerade. So we have gerade times ungerade times gerade. Gerade times ungerade is ungerade. Ungerade times gerade is ungerade. So we can work this out through the multiplication table, just taking any two at a time. They commute and they're associative, so you can multiply the functions in any order and it won't make a difference, and you can group them any way you want. No matter how we get it, we see that the integrand of our dipole moment vector turns out to be ungerade. For a transition to be allowed, we have to get the totally symmetric representation, which is always gerade. So if we get ungerade, this tells us right away that this transition is forbidden to occur in infrared. On the other hand, if we look at the case in Raman, the ground state is gerade because it's always gerade in vibrational spectroscopy. The operator is G, it's gerade for Raman, and the excited state that we have proposed is also gerade. So gerade times gerade times gerade, not surprisingly, turns out to be gerade. Since for the transition to occur, the integrand has to equal or include the totally symmetric representation, which is gerade, this tells us that this particular transition is allowed. Now, this is part of the reason why vibrational spectroscopy is so useful, because the only time we get this situation where a transition is either allowed in Raman or IR, but not both, is when we have a center of inversion. We have a centrosymmetric molecule. And in fact, this type of application of group theory was very, very useful and important in confirming the structure of C60. At first, when the structure was first proposed, the only experimental evidence for that structure was a single peak in the mass spec, which is helpful, but it's also helpful to have as much confirming evidence as possible when we propose a new structure. And it turned out that we could predict from group theory exactly which spectroscopic transitions we should see in each particular method, whether infrared or Raman or NMR, for example. And it turned out that all of these bits of evidence were able to confirm that C60, the buckyball, actually had the structure that was proposed for it.